This chapter examines the creation and assignment of IP networks and subnetwork addresses through the use of the subnet mask, and also how devices can be grouped into subnets or smaller network groups from a large network. Implementing and managing an effective IP addressing plan ensures that networks can operate effectively and efficiently. In the original IPv4 address, there are two levels of hierarchy, a network and a host. These two levels of addressing allow for basic network groupings that facilitate in routing packets to a destination network. However, as network grows, with many organizations adding hundreds and even thousands of hosts to their network, the two-level hierarchy is insufficient. That's why subdividing a network adds a level to the network hierarchy, creating three levels: a network, a subnetwork, and a host. Introducing an additional level to the hierarchy creates additional subgroups within an IP network that facilitate faster packet delivery and added filtration, and this helps to minimize local traffic. Reasons: a flat configuration have all computers and other network devices connected to a single IP network. All devices in the organization were assigned an IP address with a matching network ID. This is not problematic in a small network with a limited number of devices. In the image we can see an example. The Dynamic Host Configuration Protocol, DHCP, is a network service that depends on broadcast. Devices send broadcasts across the network to locate the DHCP server. On a larger network, this could create a significant amount of traffic, slow network operations. If a device must process a significant amount of broadcast, it could even slow devices' operations. That's why larger networks must be segmented into smaller subnetworks, keeping them localized to smaller groups of devices and services. The process of segmenting a network by dividing it into multiple smaller network spaces is called subnetting. Subnetting can reduce overall network traffic and improve network performance by grouping devices and services into subnets that are determined by geographic location, organizational unit, device type, or any other division that makes sense for the network. Remember that a subnet is equivalent to a network. Most networks are a subnet of some larger address block. A router is necessary for devices on different networks to communicate. In a subnetted network space, this works exactly the same way. Subnetting creates multiple logical networks from a single network address. Each subnet is treated as a separate network space. Planning network subnets requires looking at the entire network and determining the main section of the network and how they will be segmented. The address plan includes deciding the needs for each subnet in terms of size, how many hosts per subnet, how host addresses will be assigned, which host will require static IP addresses, and which host can use DHCP for obtaining their addressing information. The private IP address range used on a LAN is the choice of the network administrator, and needs careful consideration to be sure that NH host addresses will be available. Knowing your IP address requirement will determine the range of host addresses you implement. Address assignment. Create standards for IP address assignments within each subnet range. Printers and servers will be assigned static IP addresses. Users will receive IP addresses from DHCP servers using /24. Subnets and routers will be assigned the first available host addresses in the range. Subnetting. All devices attached to the same network will have an IPv4 host address for that network and a common subnet mask. IPv4 subnets are created by using one or more of the host bits as network bits. This is done by extending the mask to borrow some of the bits from the host portion of the address to create additional network bits. The more host bits borrowed, the more subnets that can be defined. However, with each bit borrowed, fewer host addresses are available per subnet. Bits can only be borrowed from the host portion of the address. The network portion of the address is allocated by the service provider and cannot be changed. Subnets in use. As shown in the image, the router has two LAN segments attached to its gigabit Ethernet interfaces. To assign an IP address for each of these interfaces, it is necessary to determine the range of valid IP addresses for each subnet. A guideline to determine each of the subnets is divided in four with their unique specifications: network address, first host address, last host address, and broadcast address as shown in the image. Subnetting formulas. To calculate the number of subnets, use the formula 2 to the n, where n is equal to the number of bits borrowed. Use this formula to calculate the numbers of hosts per network. 2 to the n, where n is equal to the number of bits remaining in the host field. But because hosts cannot use the network address or broadcast address from a subnet, two of these addresses are not valid of host assignments. This means that each of the subnets has 126 valid host addresses. So, borrowing one host bit towards the network results in creating two subnets, and each subnet can have a total of 126 hosts assigned. Example: consider an internet network that requires three subnets. Using the same 192.168.1.0/24 address block, host bits must be borrowed to create at least three subnets. Borrowing a single bit will only provide two subnets. To provide more networks, more host bits must be borrowed. Calculate the number of subnets created if 2 bits are borrowed using the formula equals 2 to the 2 equals 4 subnets, as you can see in the figure number 1. Remember that all devices on the subnet will have a host IPv4 address from the range of host addresses and will use the same subnet mask. Recall that the subnet mask must change to reflect the borrowed bits. In decimal, the mask is represented as 255.255.255.192. To calculate the number of hosts, examine the local octet. After borrowing 2 bits for the subnet, there are 6 host bits remaining. Applying the host calculation formula, as shown in the second figure, we get that 2 to the 6 minus 2 equals 62 valid hosts per subnet. As shown in the third figure, the first host address for the first subnet is 192.168.1.1 and the last host address is 192.168.1.62. Consider large organizations or campuses with an internet network that requires 100 subnets. As before, to calculate the number of subnets, we must look at the number of available host bits and use the subnet calculation formula of bits borrowed minus 2. Using the IP address 192.168.10.0/24, we have 8 host bits. Calculating the number of subnets if 7 bits are borrowed equals to 128 subnets. However, calculate the number of hosts if 1 bit is remaining, the result is 0 host. If an IP network is required that has more host bits to borrow from, such as an IP address with a default subnet mask of /16 or 255.255.0.0, addresses that have a range of 128 to 191 in the first octet have this default mask. Addresses in the range have 16 bits in the network portion and 16 bits in the host portion. These 16 bits are the bits that are available to borrow for creating subnets. Using a new IP address of 172.16.0.0/16 address block, host bits must be borrowed to create at least 100 subnets. If we borrow 7 bits, we will have 128 subnets, and the subnet mask must change to reflect the borrowed bits. Subnetting will be done in the third octet, with the host bits in the third and fourth octets. After borrowing 7 bits for the subnet, there is 1 host bit remaining in the third octet, and there are 8 host bits remaining in the fourth octet. Applying the host calculation formula, we get that 2 to the 9 minus 2 equals 510 valid hosts per subnet. But remember that all 0 bits in the host portion of the address is the network address, and all ones in the host portion is a broadcast address. Therefore, there are only 510 host addresses that are actually available for each subnet. Do not forget, bits can only be borrowed from the host portion of the address. Take for example an organization that requires 1000 subnets. IP addresses that have the range of 1 to 126 in the first octet have a default mask of 255.0.0.0 or /8, which means there are 8 bits in the network portion and 24 host bits available to borrow towards subnetting. Using the 10.0.0.0/8 address block equals to 1024 subnets. When 10 bits are borrowed, the mask is extended 10 bits into the third octet. In decimal, the mask is represented as 255.255.182.0 or a /18 prefix. To calculate the number of hosts, examine the third and fourth octet. A total of 14 host bits remains. This equals to 16,382 hosts. There are two considerations when planning subnets: the number of host addresses required for each network and the number of individual subnets needed. There is an inverse relationship between the number of subnets and the number of hosts. The more bits borrowed to create subnets, the fewer host bits are available. Therefore, fewer hosts per subnet. If more host addresses are needed, more host bits are required, resulting in fewer subnets. When borrowing bits to create multiple subnets, you must leave enough host bits for the largest subnet. Sometimes, a certain number of subnets is required, with less emphasis on the number of host addresses per subnet. The key is to balance the number of subnets needed and the number of hosts required for the largest subnet. To determine the total number of hosts first, consider the total number of hosts required by the entire corporate internetwork. A block of addresses is large enough to accommodate all devices, including end-user devices, servers, intermediate devices, and router interfaces. Determine the number and size of the network. Consider the number of subnets required and the number of host addresses needed on each subnet. When designing an address scheme, you should anticipate growth in both the number of subnets and the hosts per subnet. Example: based on the network topology consisting of 5 LAN segments and 4 internetwork connections between routers, 9 subnets are required. The largest subnet requires 40 hosts. The 172.16.0.0/22 network address has 10 host bits. Because the largest subnet requires 40 hosts, a minimum of 6 host bits are needed to provide addressing for 40 hosts. 2 to the 6 equals 62 hosts. The first 4 host bits can be used to allocate subnets. 2 to the 4 equals 16. This will meet the requirements and allow for some additional growth. The new prefix length is /26, with a subnet mask of 255.255.255.192. The original 172.16.0.0/22 network was a single network with 10 host bits providing 1022 usable addresses to assign to host. By borrowing 4 host bits, 16 subnets can be created. Each subnet has 6 host bits or 62 usable host addresses per subnet. Using traditional subnetting, the same number of addresses is allocated for each subnet. If all the subnets have the same requirements for the number of hosts, this fixed size address block will be efficient. However, most often that is not the case. For example, if you require 7 subnets, 3 bits can be borrowed from the host portion in the last octet to meet the subnet requirements of 7 subnets. Borrowing 3 bits creates 8 subnets, and leaves 8 host bits with 30 usable hosts per subnet. Although this traditional subnetting meets the needs of the largest LAN, It results in significant waste of unique address. This results in 84 unique addresses. Further, this limits future growth by reducing the total number of subnets available.
Traditional subnetting creates subnets of equal size. VLSM allows a network space to be divided in unequal parts. With VLSM, the subnet mask will vary depending on how many bits have been borrowed for a particular subnet. VLSM subnetting is similar to traditional subnetting in that bits are borrowed to create subnet, but the difference is that subnetting is not a single pass activity. With VLSM, the subnet is first subnetted and then the subnets are subnetted again. This process can be repeated multiple times to create subnets of various sizes. To create smaller subnets, one of the subnets will be divided when the number of needed host address is known, and the formula 2 raised to the power of n minus 2 can be used. For example, there are 5 host bits in the address space in the image. 3 bits can be borrowed, leaving 2 bits in the host portion. The calculations at this point are exactly the same as those used for traditional subnetting. The bits are borrowed and the subnet ranges are determined. Using the VLSM subnets, the LAN and WAN segments can be addressed without unnecessary waste. In the image, the host in each of the LAN will be assigned a valid host address with the range of that subnet in 27 masks. Each of the 4 routers will have a LAN interface with a 27 subnet and a 1 or more serial interfaces with a 30 subnet. Address planning can also be accomplished using a variety of tools. One method is to use a VLSM chart to identify which blocks of addresses are available for use and which ones are already assigned. Using traditional subnetting, the first 7 addresses blocks were allocated for LANs and WANs. This scheme results in 8 subnets with 3 usable addresses each. In order to use the address space more efficiently, prefix 30 subnets are created. The last prefix 27 subnets was further subnetted to create the /30 subnets. Designing the addressing scheme in this way leaves 3 unused /27 subnets and 5 unused /30 subnets. There are 3 primary considerations when planning address allocation: preventing duplication of address. These are providing and controlling access. Some hosts, like servers, provide resources to internal and external hosts. Monitoring security and performance. Network traffic is examining for addresses that are generating or receiving excessive packets. Assigning addresses within a network. There are different types of devices, including end-user clients, server and peripherals, hosts that are accessible from the Internet, intermediary devices, and gateway. When developing an IP addressing scheme, it is recommended to have a step pattern of how addresses are allocated to each type of device. This benefits administrators when adding and removing devices. A network addressing plan might include using a different range of addresses within each subnet for each type of device. Addresses for clients. Using Dynamic Host Configuration Protocol is generally the preferred method of assigning an IP address to hosts on large networks. It reduces the burden on network support staff and virtually eliminates any errors. Another benefit is that an address is not permanently assigned to a host but is only listed for a period of time. Addresses for servers and peripherals. Any network resource, such as a server or a printer, should have a static IP address. Servers and peripherals are a concentration point for network traffic. Using a consistent numbering system for these devices makes the identification easier. Addresses for hosts that are accessible from Internet. In most Internet networks, only a few devices are accessible by hosts outside the corporation. The IP addresses for these devices should be static. In the case of servers accessible by the Internet, each of these must have a public space addresses associated with it. In some cases, all these devices are on a network that is numbered using a private address. This means that the router or firewall at the perimeter of the network must be configured to translate the internal addresses of the server into a public address. Addresses for intermediary devices. Almost all traffic within or between networks passes through some form of intermediary devices. Therefore, these network devices provide an opportune location for network management, monitoring, and security. Addresses for the gateway. Routers and firewall devices have an IP address assigned to each interface. Each interface is in a different network and serves as the gateway from the host in that network. Routers and firewall interfaces are the concentration point for traffic entering and leaving the network. These devices can play a role in network security by filtering packets based on source or destination IP address. Subnetting using the subnet ID. IPv6 subnetting requires a different approach than IPv4 subnetting. An IPv6 address space is subnetted to support hierarchical logical design of the network. An IPv6 address block with a 48 prefix has 16 bits for subnet ID. Subnetting using the 16-bit subnet ID yields a possible 65,536 prefix 64 subnets and does not require borrowing any bits from the interface ID or host portion of the addresses. Each IPv6 prefix 64 subnet contains 18 quintillion addresses, more than will ever be needed in one IP network segment. Subnets created from the subnet ID are easy to represent because there is no conversion to binary required. To determine the next available subnet, just count up in hexadecimal. The global routing prefix is the same for all subnets, only the subnet ID quarter is incremented for each subnet. IPv6 subnet allocation. With over 65,000 subnets to choose from, the task becomes one of designing a local scheme to address the network. The example topology will require subnet for each LAN as well as for the one link between router 1 and router 2. The allocation of 5 IPv6 subnets with the subnet ID field 1 through 5 will be used. In this other image, each LAN segment and one link is assigned a 64 subnet. Each 64 subnet will provide more address than will be needed. Each of the router interfaces has been configured to be on a different IPv6 subnet. Subnetting into the interface ID. Similar to borrowing bits from the host portion of an IPv4 address, with IPv6 bits can be borrowed from the interface ID to create additional IPv6 subnets. This is typically done for security reasons to create fewer hosts per subnet. When extending the subnet ID by borrowing bits from the interface ID, the best practice is to subnet on a nibble boundary. A nibble is 4 bits or 1 hexadecimal digit. Doing this reduces the size of the interface by 4 bits from 64 to 60 bits. Subnetting on a nibble boundaries means only using nibble-aligned subnet masks. This creates subnets by using the additional hexadecimal value. It is possible to subnet within a nibble boundary within an hexadecimal digit, but it is not recommended. This takes away the advantage easily determining the prefix from the interface ID. Thank you for watching.